this chapter, we're going to look at topics related to measurement. In this lesson, we're going to look at area and volume scale factors. Okay, everybody. So in this lesson, we're going to take a look at area scale factor and the volume scale factor. Okay, because I had mentioned in a previous lesson that that might be different than the linear scale factor, and that you got to pay attention to that so that you're not, I don't want to say tricked, but confused by what you're seeing. Okay, so a scale factor is just a way of describing the enlargement or reduction of an object proportionally. Okay, so big focus right now on this proportional reasoning. So the scale factor is going to be the dimension of the model divided by the dimension of the original, or new divided by old, compared to old. So now we're going to take a look at the area scale factor. And we're going to start off with rectangle A. Now, we already know, okay, the length and the width here, but that also gives us the area. Okay, so the area of rectangle A here is going to be length times width, so 3 times 2, or 6 centimeters squared. Okay, so we're going to kind of keep that in our pocket here. We know that that works. So now let's take a look at an enlargement or a reduction here. So if we go from the original here to this one, take a look at what's happened to this, the length of the size of the length here. We go from 3 to 2, and then for the width here we go from 2 to 4. So the linear scale factor here, when we go down here to compare it, we're going to go from 6, wow. Oh no, that's right, 6 compared to 3, and so it's been multiplied by a factor of 2. But here, let's take a look at the area of this one. So the area of rectangle C, well, that's going to be 6 times 4, that's 24 centimeters squared. If we compare the area scale, if we grab the area scale factor by comparing the area of the new one to the area of the old one, we notice that it's a multiple of 4. This is 4 times as big as this one. And actually, you know what? That makes total sense, because if this has been doubled, okay, if I cut that in half, that is the length of the original. Well, so is this. If I cut the width in half, that is the width of the original, okay, and so is this right here. And by just drawing those lines through, oh, well, look at that, yeah. Each one of these would be equivalent to the original here. And so that's why it's 4 times as big. This length is twice as big, this length is twice as big, so the whole area is 4 times as big. Another way of looking at it, if you want to see it this way, if I'm going to come up with the area of C, okay, to get the area of C, what it's going to be is, first of all, 2 times the length of A multiplied by 2 times the width of A. Those two 2's I can pull out front here, so this is going to be 2 times 2 times the area of A, and that is going to be 4 times the area of A. And it's really this 4 that I want to focus on, because I can pull those two factors of 2 out. Anyway, I hope that makes sense. So what we're doing here is when we know the linear scale factor, to get the area scale factor, what we did there was square it. Now let's take a look at the reduction here and just see if it's the same thing. When we go from this original rectangle to this one, okay, bear in mind the length here is now half as long as it was. The width here is half what it was. So we know, and we'll use the width here because it's easier. The width of the new one is 1, the width of the original is 2, so we've got the scale factor of a half. Now, let's figure out the area of this one. The area of D is going to be 1.5 centimeters times 1 centimeter, which really just gets us 1.5 centimeters squared. Okay, well, go to our area scale factor here. The model, the new one here, is going to be 1.5. The original was 6. Okay, so now let's do that math here. Now, I'm usually a little bit more comfortable with fractions. If this is going to be 3 over 2 divided by 6, okay, well, that's going to be 3 over 2 multiplied by 1 over 6. The 3's cancel in the 3 up here and the 6 down there, and I'm going to get 1/2 times 1/2, which is just 1/4. And notice once again, to go from the linear scale factor to the area scale factor, what did I do? I squared it. squared it. That's an interesting relationship, and you know what? It will always hold. So now let's take a look at some examples. Okay, and just to reiterate before we get into our example here, the area scale factor is related to the linear scale factor in one of the two ways here. Either the area scale factor is the square of the linear scale factor, or the square root of the area scale factor is the linear scale factor. Anyway, there's a square that's happening there to go from one to the other. So let's take a look at our first example here. It says Maggie has scanned an 8-inch by 10-inch photograph on her computer. Maggie would like to increase the area by 44%. Determine the area scale factor and the linear scale factor. Okay, well, if she's going to increase the area by 44%, what that means is we're going to take the area, okay, and we're going to have to multiply it by 1.44. Now, just to explain where I got that from, what that's going to be is we're going to take the area of the original and we're going to add to that 44% of that area. Because sometimes people don't understand what I mean when I go 1.44. So this is the area of the original plus, and then we're going to find 44% of it. You can factor out the a and you're left with 1 plus 0.44, and that's really how we're getting that 1.44 there. So my area scale factor, okay, my area scale factor is going to be 1.44. Okay, so maybe we'll say that here. My area scale factor is going to be 1.44. So now if we want the linear scale factor, that's going to be the square root of the area scale factor. Okay, that's the relationship that we've established. So that is going to be the square root of 1.44. And on my calculator, okay, we'll go the square root of 1.44, and we get a linear scale factor of 1.2. Now, notice that that is slightly bigger than 1, which means that this is an enlargement, which is totally kind of confirms what the question has stated here. We're increasing the area by 44%. So now the next part of this question is calculate the area the printer must cover with ink. Okay, well, we know that the area here, the area of the original, was going to be 8 inches multiplied by 10 inches. Okay, so that's just going to be 80 inches squared. So there's the area of the original. To get the new one, the area of the new one, what we're going to do here, I'm going to use that, I'm going to multiply by the conversion factor here. So I'm going to take the area of the old and I'm going to multiply it by our area scale factor. So it's going to be 80 inches squared multiplied by 1.44. Okay. And so, pull out the calculator, whoops, 80 multiplied by 1.44. Okay, and so the new area is going to be 115.2 inches squared. And now we go to this one. Maggie must also produce a print whose area will be reduced by 25%. Determine the dimensions of the print to the nearest hundredth of an inch. Okay, now we got to be careful with this one, okay? Because this one is asking us to take a couple steps here that might not be obvious right off the bat here. So first of all, we're going to reduce the area by 25%. That means what we're going to do here is the area, okay, the new area is going to be the area of the old minus 25% of the area of the old. It's really important that you catch that we're not finding 25% of the area, we're reducing it by 25%, which means when you factor out the original area, that's going to be 1 minus 0.25, and for some of you, you probably just did this in your head real quick. This really means that it's a 75%, sorry, the area that we're finding is 75% of the original. Okay, that's the new area here. Now, that means, okay, based on how I interpret this, that means that my area scale factor here is going to be 0.75. So if I want the linear scale factor, it's going to be the square root of 0.75. Okay? And so, actually, I can leave it like that. I'll just leave it like that, although maybe I'll give you a decimal equivalent. Okay, so square root of 0.75 is going to be roughly 0.8, let's say 0.87. So this will be approximately 0.87, just to give you a sense of what we're doing there. Now, in order to figure out what the dimensions are, I'm going to take the new, let's say, width is going to be the old width multiplied by 0.87. You know what? No, let's not do that. Let's not multiply by 0.87. Let's do it exactly here. Let's say the square root of 0.75. So that is going to be, well, our old width was 8 times the square root of 0.75. Okay, so, whoops, let's clear that out here. 8 multiplied by the square root of 0.75, 6.9. 6.9 inches. The new length is going to be the old length multiplied by the square root of 0.75. So that will be 10 multiplied by the square root of 0.75. And we just pull out the calculator and we do that again. 10 times the square root of 0.75, 8.7. Approximately. In both cases, these are approximate. Okay, and so those are the dimensions of the new print to the nearest, oh shoot, hundredth of an inch. I didn't see that. So, darn. So this is going to be, I can do this one easily. That's 6.93. This is going to be 8.66. Should have paid more attention to that. There we go. Oh, and you can't see that even. I'm sorry. Oh, I really fouled that up. Anyway, there you go. Right, in this question we read that the area of the province of Alberta is approximately 661,850 kilometers. On a map, the area of Alberta is represented by 264.74 centimeters squared. So the scale of the map, the linear scale factor, okay, and we got to remember that that's what they're asking for here, can be written in the form 1 centimeter to x kilometers. So what's the value of x? Okay, so we're trying to get a linear scale factor here, but we're given the two areas. So what we're going to do here is get the area scale factor first. Okay, and so what we'll do here is our model here is going to be 264.74 divided by 661,850. Okay, and when we do that, let's figure that out here. So on my calculator, that's going to be 264.74 divided by 661,850. Oh, now look at that number there. Now that means 4 times 10 to the negative 4, so the decimal moves over, but it's actually a really nice decimal. Let me convert that to a fraction here. That's okay, that's just 1 over 2,500. That's actually a really nice number, because what that means is if I want to convert that to our linear scale factor, I'm just going to take the square root of the area scale factor, which in this case is going to be the square root of 1 over 2,500. And if I take the square root of that, square root of my answer there, I get this beautiful 1 over 50. Now, what that means is, based on how this whole question is kind of developed here, remember, this is the area of the model over the area of the original, model over the original. Now, but this is in squared units. As soon as I took the square root of that, it became linear units. So this is 1 centimeter is 50 kilometers. So therefore, x is equal to 50. That worked out really nicely. I like that. Okay. Now, oh, sorry, the scale factor over here, our linear scale factor was going to be 1 centimeter to 50 kilometers, which meant 1 centimeter squared was equal to 2,000, whoops, I'll do it like this with a colon there, 2,500 kilometers squared. Now this one here, on the same map, the area of British Columbia is represented by 376.839 centimeters squared. Determine the actual area of British Columbia to the nearest 100 square kilometers. Okay, well, we want to go from new to old here. So in terms of area, and I'll do it with a proportion here because I prefer the proportion for questions like this one. 1 centimeter squared over 2,500 kilometers squared. And on our map here, we have British Columbia is 376.839 centimeters squared over x kilometers squared. And now I'll cross multiply and divide, but 1 times x, that's beautiful. Our centimeters squared are going to cancel, but I'm going to be left with 2,500 multiplied by 376.839, and this will be kilometers squared. And that works out to be, let's just plug that in, 2,500 multiplied by 376.839. Okay, and we get 942,097. That says to the nearest 100 square kilometers. Okay, so 0.5 kilometers squared, and then I'll round that to the nearest 100. So 42100 kilometers squared. Okay, that's the answer that they're looking for. Okay, so this next problem reads, the area of a circle is 50 centimeters squared. So, okay, the area is 50 centimeters squared. A second circle has a radius that's 3 times the radius of the first circle. What's the area of the second circle? Okay, well, we know that the linear scale factor is 3, and because of that, I know that the area scale factor has to be this value squared. So this has got to be 3 squared, or 9. So the area's got to be 9 times that. So the area of, let's say, circle 2 is going to be the area of circle 1 multiplied by our area scale factor, or 9. So this is going to be 50 centimeters squared times 9, or 450 centimeters squared. Okay, so once you know what the linear scale factor is, I don't actually have to go through the process of finding the original radius, which I could have done. Okay, I can just immediately compare the areas. So this next question says, consider the triangle to the left, okay, right here. So that's a 3, 4, 5 triangle. A new triangle to the right. We've only got the dimension 8 here, but it's between A and B. Now I assume that this probably should have been like A primed, B primed, and C primed. But there we go. It has a base of 8. Determine the area of the new triangle in exact form without calculating the other 2 sides to the nearest 10th. Okay, well that's fine. We can do that. Because what we're doing here is we're comparing, first of all, we got to figure out what the linear scale factor is. Now, I'm assuming that the 2 triangles are meant to kind of match up here. So we've got this, the linear scale factor here is going to be the new base divided by the old base. Okay? Well, our new base is 8 and our old base is 3. So that's going to be our linear scale factor. Now, that means, therefore, that my area scale factor is simply going to be that scale factor squared. So it's going to be the linear scale factor squared. So 64 over 9. That's what I need to know here. So once I have the area of the original, I just have to multiply it by this to get the area of the new one. So the area of this one, the area of our original, let's say, is going to be 1/2 base times height. Whoops. Sorry, I wanted to do that with variables before I plugged in the numbers. So 1/2 base times height. So this will be 1/2 3 times 4. 3 times 4 is 12, divided by 2 is 6, so 6 centimeters squared. So the area of the new one is going to be the area of the old one multiplied by our area scale factor. So 6 multiplied by 64 over 9. Okay, well, there's a factor of 3 that the 9 and the 6 share, so I can cancel that out. But that's going to leave me with 2 times 64. And then there's going to be a 3 left over in the denominator. So 128 over 3 centimeters squared. That will be the area of our new triangle. So this next question reads, 2 cubic boxes to the right. Okay, and so this one's got 50 up, this one's 40 up, are mathematically similar and have to be wrapped with decorative paper. If the larger box requires 3.27 meters squared of wrapping paper, that's the surface area, okay, and that's important, okay, we're not talking about volume here, we're talking about surface area. Calculate amount of paper needed to cover the smaller box to the nearest 10th. Okay, well, we know the area of this one right here, so I'm going to use that in a bit here. What I got to do is figure out my area scale factor. Okay, well, to do that, I'm going to figure out my linear scale factor. And I'm going to use the small one as the new one, so it's going to be the area of the new divided by the area of the old. Wow, not the area. Did I do that before? Okay, no. Sorry, I thought I screwed that up here. I was thinking the right thing, but I should say that, let's say the height of the new divided by the height of the old. So that's going to be 40 over 50. Or we've got this linear scale factor of 4/5, which means, therefore, my area scale factor is going to be the square of that, or 16/25. So now, if I know the surface area of the original, I can figure out the surface area of the new one. And we happen to have the surface area of the original. So we know that the surface area of the new one is going to be the old one multiplied by 16/25, and that will be 3.27 meters squared multiplied by 16/25. Now we just go to the calculator. So 3.27 times 16/25. And to the nearest tenth, we get 2.1. So it's approximately 2.1 meters squared. Now in this next section, we want to take a quick look at the volume scale factor. We're going to do that by comparing these two rectangles here. So really quickly, okay, we've got the dimensions here. This is the height, this is the length, this is the width. So we're just going to pick a dimension here. We're going to assume that these are expanded by or enlarged by the same amount. Okay, so we'll take our new height here compared to our old height. So that's going to be 4 divided by 2. So in terms of the linear scale factor, to go from here to here, we multiplied by 2. Okay, now the area scale factor, we already know that that's going to be the square of that. So I don't even need to really worry about, I don't need to worry about finding out the surface area of both of those. I could. It's just kind of a lengthy computation. It's not hard. It's just long. But I already know that's going to be 4. Now, based on that pattern, I can probably guess what this volume scale factor is, but let's just take a look at it. The volume here is going to be length times width times height. So it's going to be, I don't know why I wanted to write it like that. This is going to be 24 centimeters cubed. Over here, our volume is going to be length times width times height. Okay, and so that's going to be 8 times 6 times 4, 192 centimeters cubed. So when I put those in, 192 over 24, when I divide those, 192 divided by 24, you can probably guess what this turns out to be. It's going to be 8. So how do I get 8 here? What's the kind of the shortcut? Well, to go from here to here, I squared it. To go from here to here, what am I going to do? I'm going to cube it. That's the rule. In fact, that's what we're looking at right here. The volume scale factor is the cube of the linear scale factor, or another way of writing that is the cube root of the volume scale factor is going to be the linear scale factor. Okay, so this question says, consider the rectangular prism on the right. So 2, 3, 6. Okay, given that the volume is length times width times height, the cube has a volume of 36 centimeters cubed. Fill in the missing values on the table. Okay. So what we've got here is, when we look at this here, basically what we're doing is we're creating new shapes here. So our scale factor, we're just going to go 1 to 3, which means each of these is going to get multiplied by 3. So that'll be 18 centimeters. Okay, this will be 9 centimeters and 6 centimeters. But what that means is for my volume, if I'm multiplying by 3 for my scale factor, what I'm going to end up doing here is multiplying this by 27, 3 cubed. Okay, so 36 times 3 cubed. And when I do that, I get 972 centimeters cubed. Now, I'm just going to double check that by multiplying 18 by 9 by 6. And yeah, that's what you get here. When you multiply these three together, you get 972. So it's a bit of a shortcut here. So what our volume scale factor is going to be 3 cubed, or 27. That's what I multiplied by. This next one here, I am multiplying by a half for my linear scale factor, which means this is going to end up being 3 centimeters, 3 over 2 centimeters, or 1.5 if you'd rather use decimals. And then 2 centimeters is just going to be 1 centimeter. Now, when I go from the linear scale factor to the volume scale factor, I'm gonna cube this. Okay, so 1/2 cubed is going to be 1/8. So 36 times 1 divided by 8, and I am getting 4.5, or what ends up being 9 over 2 centimeters cubed. Okay, now let's just double check that. Let's just see if that works. What is 3, maybe I'll do this in front of you guys here. What is 3 times 1.5, that's the 3 over 2, times 1? The answer is 4.5. Convert that to a fraction, 9 over 2. So yeah, my volume scale factor here is going to be 1/2 cubed, or 1/8. Now for these next two here, basically all we're doing is we're hiding the scale factors over here. So notice I'm going from a width of 3 to 15, which simply means I'm multiplying by 5. So 6 times 5 is going to be 30 centimeters, and 2 times 5 is going to be 10 centimeters. Now, if my linear scale factor is 5, that means my volume scale factor is going to be 5 cubed, or 125. Okay? So if my original volume was 36, so 36, I'm going to multiply by 125 to get my new one, which is 4,500. Okay, now let's just double check that that works here. Let's multiply these three dimensions together and see if we get the same value. So 30 times 15 times 10, and I do. I get 4,500. Good. Here, I went from 6 to 0.6. Oy, that means I divided by 10. So 3 divided by 10 is going to be 0.3 centimeters. 2 divided by 10 will be 0.2 centimeters. Now, to get my volume scale factor, I'm going to cube that, which is going to end up being 1 over 1,000. Okay, which basically means I'm just going to move the decimal. So if here's my old volume, I'm going to move the decimal 3 places to the left there, which is going to be 0.036 centimeters cubed. Now let's just double check that. Does that happen? When I multiply 0.6 times 0.3 times 0.2, whoops, no, that's not going to work. 0.6 times 0.3 times 0.2, do I get that? And I do, 0.036 centimeters cubed. Right, in this next question we read, Axis Globes Limited produces globes with a diameter of 30 centimeters. Isabel, the manager of Axis, has her employees construct a globe to put on the roof of their building with a diameter of 1.5 meters. Okay, now notice, I mean, these are the values, the measurements that we're given here. Notice that their units are different here. Okay, that's going to be significant in a second here. It says calculate the linear scale factor of the globes. If I want to calculate the linear scale factor, what I need to do here is make sure that we're talking about the same thing. Okay, particularly when I move to the volume one. I just want that to be really a clean value at the end here without having to worry about units. Just what do I have to multiply to get the new volume or whatever it is I'm looking for here. So my new compared to old here, let's do these both. It doesn't matter. We just got to choose. Is it going to be centimeters or is it going to be meters? I tell you what. Let's go with centimeters here, just because it's going to make the numbers a little bit nicer to work with. So 1.5 meters is going to be 150 centimeters divided by 30 centimeters, and so the answer is we've got a linear scale factor of 5. What's nice about that number is if I don't worry about the units, it can be whatever unit you want. I could actually make this inches and I'd still be multiplying by 5 because there's no units here. It's just a multiple of 5. Now, if I want to know what the volume scale factor is, I'm going to take the linear scale factor and I'm going to cube it to get the volume scale factor. In that case, it's going to be 5 cubed is equal to the volume scale factor, or 125. And again, this is going to be independent of the units. It doesn't matter. Whatever unit I used to measure volume for in the original, I'll just multiply that by 125. A supermarket sells cylindrical cookie jars, which are mathematically similar. The smaller jar has a height of 15. Okay, there it is. And the volume of 750 centimeters cubed. The larger jar has a height of 24 centimeters. Calculate the volume of the larger jar. Okay, well, all I need to do, first of all, is get that linear scale factor, right? And so our linear scale factor is going to be, let's say, the height of the new divided by the height of the old. And so the height of my new here, we were told, was 24 centimeters. And the height of my old was 15 centimeters. The centimeters will cancel here. There's a factor of 3 that's common, so this is going to become 8/5. Okay, so that's my linear scale factor. And we know that the volume scale factor will be the linear scale factor cubed. So that'll be 8/5 cubed. Okay, and so 8 cubed is going to be 512, and 5 cubed is 125. Oh, I like the fact that the numbers are the same there, just in a different order. I like that. Sorry, had to comment on that. Anyway, so now we're going to calculate the volume of the larger jar. Well, the volume of the larger jar here, we already know is going to be the volume of the original multiplied by our scale factor here, 512 over 125. And this will be the volume of the new one. And the volume of the original was 750 centimeters cubed. Okay, over 125. This will be the volume of the new. So now I'm just going to pull out the calculator here. 750 multiplied by 512 divided by 125. Oh, and we get a really kind of a nice clean number there. 3,072 centimeters cubed.